Let's talk through this word problem that's a real-life situation where we have a traffic flow of cars per hour going across an intersection. Now, it's given by this kind of complex-looking function here, where we've defined t to be number of hours, where t equals 0 corresponds with 6 a.m. Our end goal is to figure out how many cars pass through this intersection between 6 a.m. and 10 a.m. So I think usually the work here isn't that difficult for students. The setting it up or conceptualizing what are we actually figuring out, that's the difficult part. So let's talk about that a little bit. If we think about this as being a graph, t is our variable, so that's going to go along what would normally be the x-axis. And t corresponds with number of hours from 6 a.m. on. So we're kind of looking at 0 corresponding with 6 a.m. And we're looking to get to 10 a.m., but 10 a.m. is 4 hours after 6 a.m., so we're looking between 0 and 4. Now we're told that it's a traffic flow of cars per hour, so our units are kind of cars per hour on what would normally be the y-axis. In this case, it's kind of the r of t axis. And t is our number of hours. So in this case, our function is a little bit difficult, but let's break it down. If it was a simple constant function, it would look something like this, going straight across. And let's say we were getting 10 cars per hour. Our end goal would be figure out 10 cars per hour, and we'd multiply that by however many hours we're looking at. So in our case, it would be 4 hours. What this really is it's calculating what's the area under the curve down to the t-axis, I guess, in our case. And, that's length times width. That's a rectangle that we're looking at there. The calculation is going to be pretty easy. 10 cars per hour multiplied by 4 hours. Our units are going to simplify, and we would get this to be, 10 times 4 is 40 cars. Now, the units work the same with our more complex-looking function, but it's not a simple rectangle, unfortunately. So let's back up and think about what ours is going to look like, and kind of go with the same idea that we want to find the area under the curve. So in our case, because we have a negative out here with the highest power of t, this is going to be a quadratic function, a parabola that's opening downwards. So in our case, this kind of goes up here and comes down. It works out that our t-intercepts, or like x-intercepts here, are about negative 0.25 and positive 4.5. I used a calculator to help me find those. Well, our end goal is going from 0 to 4. We're cut off here at 4, and we're cut off here with kind of the y-axis for 0. So the goal, find the area underneath this curve. All right, well, that's where integrals come in, play a part. This is actually not that difficult to find the area between the curve and the x-axis, or t-axis in our case, by using an integral. Now our bounds are going to be from 0 to 4. Our function is going to be that r of t, which is 300 plus 900t minus 210t squared. Now our variable is t, so we're going to use a dt at the end. Okay, next what we want to do is go ahead and do the integration. So to integrate the 300, it's a constant, we need to put a t with it. We could check this by taking the derivative of 300t. That derivative would just give us back the 300. Moving on to that next term, we have 900. That constant comes along. We'll bring the t along. Now the t in the original problem has an exponent of 1. We're going to use the power rule here and add 1 to our original exponent, giving us a new exponent of 2. Next, we divide by that new exponent of 2. And now you tend to put these just under the constant because it is a constant, so it'll be 900 divided by 2. Moving on to the last term, we're going to bring along the minus 210, and then we'll have a t with this term as well. Again, we use the old exponent, we increase it by 1, so 2 plus 1 is going to make 3 for our new exponent, and then we divide by that new exponent. Now all of this has to be evaluated between 0 and 4, our bounds of integration. So to do this, fundamental theorem of calculus says we go ahead and we're going to replace each of our variables, t in this case, with the upper bound first. So 300 times 4 instead of t, plus, if you're okay with it, I'm doing 900 divided by 2 in my head, makes 450. Replace the t with the 4, this time it's squared, minus 210 divided by 3 makes 70. And then replace the t with 4. This time it's cubed. Minus, now we go ahead and replace each of the t's with 0, our lower bound. So in this case, 300 times 0, plus again 450 times 0 squared, minus 70 times 0 cubed. Now lucky for us, when you multiply by 0 or 0 squared or 0 cubed, all the end part here becomes 0. Like that entire big set of parentheses back there is subtracting 0. So we don't have to really worry about that part. From here, it's just a little bit of computations. We're going to do 1200, 300 times 4, plus 450 times 16 is 4 squared, makes 7200, minus 70 times 4 cubed is 64, works out to be 4,480. Combine these together, we get 3,920. And remember, our units were going to be number of cars. All right, hope this helps out. I kind of ignored that minus 0 at the end because really it's not going to affect our computation here when we get finished. So hope this works out and helps you understand this problem a little bit better. Remember, this 40 cars that I got in the example was when I said it was a constant function going straight across. Our actual answer is going to be this 3,920 cars total. All right, hope this helps. Good luck.